In this lecture, we will derive Laplace and Poisson's equation for electrostatics. So in our previous lectures, we have seen that there are two specific Maxwell equations which are satisfied by an electrostatic field, and these are, first is the divergence equation and the other one is the curl equation. So we already know that an electrostatic field, let us say this is an electrostatic field, so we know that its curl will be equal to 0 for electrostatics. And we have seen, according to Helmholtz theorem, that a curl-free field can be represented by a gradient of a scalar quantity, and we call that quantity as the potential. We also have seen that the divergence of electric flux density gives us the free charge density. Now for a vacuum media, we know that this D is equal to epsilon naught E. Now I will put the value of D in terms of electric field intensity in this divergence part. So del dot epsilon naught E is equal to rho free, or the source charge density. Now since this epsilon naught is a constant with respect to the space coordinates, so we can take it outside this divergence. So del dot E is equal to rho free. Furthermore, we know that E is equal to minus of gradient of the potential. I will put that. So this equation will become epsilon naught, minus sign I will take outside and take it to the right hand side. So this equation becomes epsilon naught del dot del phi. Now this is the Laplacian operator. Del square phi is equal to minus rho by epsilon naught, where rho means the source charge density. In coulomb per meter cube. So this equation is known as Poisson's equation. Now whenever there is no source charge density, then the right hand side of this equation will be equal to 0. So del square phi will become equal to 0. So this special case gives us the Laplace equation. So these two equations are very important for electrostatics, because if we know how to solve these equations, then we can get the potential distribution, and from that we can get the electrostatic field just by taking the gradient of that electrostatic potential. So we should know, at least for some cases, how to solve such equations. Now in Cartesian form, I can write this Laplacian as dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So we see that the Laplace equation becomes dou square by dou x square of phi plus dou square by dou y square of phi plus dou square by dou z square of phi should be equal to 0. This is in the Cartesian form. For other curvilinear coordinate system, this form will be a little complicated, and we will try to derive for at least the spherical coordinate system. So we will now derive this Laplace equation in spherical coordinate system in the next slide. Now we have seen that we can write gradient in a general form for any coordinate system as del is equal to dou by dou u1 multiplied by the first metric coefficient plus dou by dou u2 the second metric coefficient plus dou by dou u3 the third metric coefficient. I have told what are the values of these metric coefficients for all the curvilinear coordinate system which we are going to need. So I advise you to study the coordinate system which I have already taught in my previous lectures. Now for spherical coordinate system, r, theta, phi we know that h1 is equal to 1, h2 is equal to r, and h3 is equal to r sine theta, and u1 is equal to r, u2 is equal to theta, and u3 is equal to phi. Now we have also seen that divergence in a general coordinate system can be written as del dot A, where A is a vector with its component given as A1 in AU1 direction, A2 in AU2 direction, and A3 in AU3 direction. In general terms, it can be written as 1 by H1, H2, H3 dou by dou U1 of H2, H3, A1 plus dou by dou U2 of H1, H3, A2 plus dou by dou U3 of H1, H2, A3. This general equation also I have derived or given the way to derive this general equation for divergence in one of my previous lectures. So now we will utilize these two forms, these two general forms specifically for spherical coordinate system to derive the Laplace or Poisson's equation in spherical coordinate system. So what we need to do, we need to find divergence of gradient of phi in spherical coordinate system. So first we will find the gradient. So gradient of phi in spherical coordinate system from this equation can be written as dou by h1 is 1, dou u1 of phi means dou r of phi in direction ar, and since gradient is a vector operator, so these are the components of a vector. We should remember this. Plus dou by h2. Now h2 is r dou theta phi a theta plus dou by h3 is now r sine theta dou phi in direction of a phi. Now to avoid confusing between this directional coordinate phi and the potential phi, I will write phi as v so that we do not get confused with these two symbols. Now I will put the value of the gradient of this potential to find its divergence. That we will do in the next slide. So now we want to find the divergence of this vector, and the vector is dou by dou r ar v plus 1 by r a theta dou by dou theta v plus 1 by r sine theta a phi dou by dou phi of v. Now we will use the general system equation which we have derived in one of our previous lectures and which I have written on the previous slide for the divergence. So I will put the value of divergence now. I will get 1 by r into r sine theta into dou by dou r h2 h3 r square sine theta dou by dou r of v plus dou by dou theta. Now it will come h1 h3, h1 is 1, h3 is r sine theta dou by dou theta of v plus dou by dou phi. Now here it will come h1 h2, h1 is 1, h2 is just r into 1 by r sine theta dou by dou phi of v. Now we need to solve it further. So this is equal to 1 by r square dou by dou r. Now this sine theta can be taken inside because it is not depending on r. and on solving we will have r square dou v by dou r plus 1 by r square sine theta. This r square sine theta I have taken inside here. Now this r will get cancelled out. Dou by dou theta of sine theta dou v by dou theta plus this r will get cancelled out, and the sine theta can come outside. 1 by r square sine square theta dou by dou phi of dou v by dou phi. So it will give dou square v by dou phi square. So this is equal to del square v. So we know now that it can be written equal to 0 if it is Laplace equation, or if it is having some source charge density, then it is equal to minus of rho by epsilon naught. So we can write it as, for Laplace, del square v is equal to 0 is equal to 1 by r square dou by dou r square dou v by dou r plus 1 by r square sine theta dou by dou theta of sine theta dou v by dou r, not dou r, dou theta, plus 1 by r square sine square theta dou square v by dou phi square. So in this way we have derived this Laplace equation in spherical coordinate system. Now I will leave this as an exercise to derive this Laplace equation in cylindrical coordinate system. This is the process is very same or similar to the procedure which we have just used, and we can easily find it. Now for the final checking on the answer, I will write the final equation in cylindrical coordinate system, and it comes out to be del square v is equal to 0 equal to 1 by r dou by dou r dou v by dou r plus 1 by r square dou square v by dou phi square plus dou square v by dou z square, where cylindrical coordinate system consists of r, phi and z. I should tell you that for this case, this is a u1 or u1, this is u2 and this is u3, and h1 will be equal to 1, h2 equal to r, and h3 is equal to 1. So I told everything which you should know. Now we just need to apply the general form of the gradient as well as the divergence which we have written in the previous slides, and we can directly get the cylindrical form coordinate system form of the Laplace equation as well as the Poisson's equation. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join us in our Telegram group whose link is given in the description of this video. Thank you.